to ask the questions. What we have found quite successful in recent lectures is if there are things that you don't understand as the lecture goes on, please feel free to type them into the chat box. And there we go. There's right on cue. The first question comes into the chat box. Are we meant to be able to see the prof? Well, I can see me, Sharon, and I think my camera's on.
We can see you there.
I should appear to you in a small sort of postage stamp in the bottom right-hand corner of your screen.
I suspect that the question really is asking, are we meant to be seeing slides? The slides
will start shortly, Sharon. Yes, the slides will start shortly. The main screen picture is of tonight's speaker. So thank you for the prompt, because it allows me to introduce Dr. Mark Norris, who is one of our own lecturers in astrophysics here in the JHI, and you've probably heard enough of me already now, so I'll move straight on and say he's an expert in galaxies, galaxy formation and evolution, and special sorts of galaxies that he'll tell you all about. And he's taken as his title for this evening, Hunting for the Ghosts of Galaxies. So I hope you all enjoy your evening, and over to you, Mark.
Can I just make one announcement very quickly? We are recording at the moment. So if you're uncomfortable with being recorded at the end, please don't turn your camera on. Thank you.
All right, let's get sharing my screen. And at the minute, you should only see me. Hopefully, you can see my slides now. Is that correct? Can people see that?
Yes.
Yes.
Brilliant. Very good. So yes, as Derek said, I am particularly interested in the formation and evolution of galaxies. And I don't think that that's particularly unusual. For as long as there have been humans on Earth, and they've been, anatomically anatomically identical to us humans on Earth for over 100,000 years, I'm sure they've looked up at the night sky and wondered, what were those twinkling points of light, and what was that ghostly band of light that arcs across the sky? Of course, a ghostly band of light that we have a lot more trouble seeing these days because of light pollution, but nevertheless, it's still there. Now, as the telescope was invented, going back now, 500 years-ish, that allowed us to begin to resolve that ghostly glow across the sky that we, of course, call the Milky Way, and to realize that, in fact, that ghostly glow is the light of millions and, in fact, billions of individual stars that just happen to be so far away that their light, when combined together, gives you this diffuse glow. And when you have a powerful enough telescope, you're able to resolve that light into the individual stars. And so nowadays, with the technology we have at our fingertips, we know that the Milky Way galaxy, in fact, is composed of around 200 billion stars. Now, what we're seeing here is a zoom in to the center of the Milky Way galaxy, just to try and kind of impress on you just how many stars that really is. So 200 billion stars in the Milky Way galaxy. But actually, we're coming up to a bit of a milestone in the development of astrophysics, because it's actually less than 100 years since we worked out that our galaxy was not the only galaxy. Up until the 1920s, there was a big debate about these other smudges that were seen in the night sky. And on one side were people that said those smudges were just gas clouds inside our own Milky Way, and the Milky Way galaxy itself was the entire universe. It took until the late 1920s, in fact, that Edwin Hubble was able to measure the distances to these, what were then known as spiral nebulae, and to work out that they were in fact at very, very large distances, and that they therefore must be galaxies like the Milky Way, but even further away. And again, using our modern technology, we've been able to determine that the universe is obviously just full of galaxies. So this is a nice animation that I really like, because what we're going to do here is zoom in to a blank patch of the sky. It was deliberately chosen because there was nothing there. There were no bright stars and there were no known galaxies. And then the Hubble Space Telescope was pointed at that patch of sky, and over a period of about a month took one of the deepest images of the sky ever. And this is what it saw. Everything you see in this image is a galaxy. And you can see that they come in all different shapes and sizes, and that they're spread throughout space. And just based on that little patch of sky, we know that there are, in that region, 20,000 large galaxies. And if you multiply that across the whole night sky, you get a number of large galaxies across the whole night sky of something like 200 billion galaxies in our observable universe. Not even the entire universe, just the bit of it we can see. So ever since that discovery that galaxies are common and that they're spread throughout space, one of the driving goals of astrophysics has, of course, been to understand how it is we get galaxies. How is it in particular now that the question is usually framed as, how is it we go from the very simple initial conditions that we know existed after the Big Bang to the multitude of different galaxy types that we see today? How is it that the universe increases in complexity with time? And that's what these little squares show. They're different snapshots of a simulation, which we'll see more of later, showing how structures evolve with time over the lifetime of the universe. Now, traditionally in astrophysics, we've had this very strong bias that breakthroughs have really depended on technological breakthroughs. So that would always be very much pointed towards the observational science as well. So new technologies, for example, would give you new views of the universe in different wavelengths of light. And as the image at the bottom shows, if you can look at the same object in different wavelengths of light, you can in fact get an incredibly different view of the object that you're seeing. So the image on the left is an image of the Andromeda Galaxy, the biggest nearby galaxy to the Milky Way. And that's probably the image that you would all recognize, because that is the optical image, the image that would be made by our eyes if we could collect enough light. The next image along, though, is the light given out by infrared radiation, or light at infrared radiation wavelengths. And so that's the light that's actually being given out by gas clouds. And so with and dust in those gas clouds. So that map there is really giving you a map, an image of not where the starlight is, but where the dust and gas that turns into stars might be. And then the final image is X-rays, and that's actually telling you about the highly energetic things going on in galaxies. So that's being given out by black holes and neutron stars and supernova remnants and things like that. And so three different views of the same galaxy, three totally different insights into how that galaxy is formed and what it's composed of. So that's really how astrophysics has worked. We invent a new technology, we look in a new wavelength, or we build a new telescope which can survey a much larger region of the sky faster, and then we find new things almost always by accident. There's very few objects that people theoretically predicted in advance. Most of the time, people just stumbled across them, and then theorists would sort of run away and try and come up with an explanation of what this object must be. But in the last few years, I, even as a proud observational astronomer, would say things have started to change. Because of increasing computer power, simulations, particularly these large-scale cosmological simulations, are becoming really very detailed. So the image on the left is showing you the distribution of dark matter in a large volume of the universe, and the image on the right is the corresponding temperature of gas in the simulation at the same time. And what you can see is this simulation is finding over time that growth of structure that we see in the universe, the appearance of galaxies in these what we call filaments and along these nodes, which we call galaxy clusters. And these simulations now are able to do some quite impressive things. For example, you can see there that there are regions where the gas temperature is rising very rapidly, and they are the regions where galaxies are forming many stars very rapidly, having a lot of supernova and pumping a lot of energy back into the gas of the universe and heating it up. So probably over the past 20 years or so, these simulations have got more and more refined, they've got higher and higher resolution, and they're now beginning to approach the resolution where they can actually, from nothing more than pure physics and an understanding of the initial conditions of the Big Bang, they can at the end spit out some objects that look like real galaxies. So this is a sort of a collage of simulated galaxies that came out of one of these simulations. And this is actually quite an old one now, it's 6-7 years old, but you are already able to reproduce objects in your simulation that look very much like modern galaxies, or galaxies as we see them today. And if you're able to do that, that probably is telling you that they're capturing most of the important physics that goes into the galaxy formation process. And one of the interesting things that's come out of this process of trying to get simulations to look more and more like the real universe is they're beginning to come up with predictions for phenomena that we actually can't observe or haven't been able to observe because it's practically very difficult. So one insight that's come about through this simulation process married together with the observations is that you really have to think about galaxy formation in terms of two completely distinct but related processes. And the first is the one we would all think about if you're talking about a galaxy being formed. And that's the star formation process. That's the process where gas, like here in the Orion Nebula, as imaged by our telescope at Alston, where gas is concentrated and collapses down under its own gravity and turns itself into stars. The chemical enrichment history is the process whereby subsequent generations of stars are more and more chemically complex because the stars that lived before them produced heavier and heavier elements during their lives and during their deaths. And so what you will see over the lifetime of the universe is that the chemical complexity of the universe increases, and in particular in the galaxies. So this is the process that you would sort of naively think of as the galaxy formation process. It's gas turning into stars. But it turns out it's really only half the picture, and in fact it's less than half the picture for some galaxies. Because there's a distinctly different effect, which is the assembly history. And that's the idea that just because you find stars in a galaxy today does not mean that they were born in that galaxy. The star formation and galaxy formation process is a very dynamic process, and it involves the interactions and merger of multiple galaxies. And you really have to understand that process if you're to get a handle on just how is it we end up with the galaxies we have today. So this simulation shows it quite nicely. This is, again, one of these large-scale cosmological simulations, and we're going to start from just after the Big Bang. And there's just about, you can see some slightly darker regions in this image. And as the simulation goes on, we just let gravity do its thing. And the regions that had slightly excess matter early on, because of fluctuations created in the Big Bang, they have slightly more gravity. And because they have more gravity, they can attract more matter. So the rich get richer. The regions with more mass are able to pull in more and more mass. And so now the animation is switching to show you the gas distribution, and the gas gets pulled along with the dark matter. And what you can see is the beginnings of a Milky Way sized galaxy. But you can see that that galaxy is not just some gas smoothly flowing in to create the stars of that disk galaxy. It's actually some of that going on, but also you can see lots of little galaxies that keep flying by, interacting with the bigger galaxy, sometimes actually colliding with it, being destroyed, and then adding their material to the growing galaxy. So you could see in this one simulation the two effects. There are some stars that are being born in that disk of that spiral galaxy, and then there are others that are actually coming in and being added to it through pure gravitational attraction, really. They were originally in distinct galaxies, but nowadays you will find them in the bigger galaxy. And so this is actually a vital part of how galaxies form. And we sometimes talk about galaxy formation as being a hierarchical process. The largest galaxies are actually built up from smaller galaxies, and the bigger galaxies will have eaten more small galaxies. And so this image here is what's known as a merger tree. Every dot on that plot is, or at least every line on that plot, shows an individual galaxy and its mass at a given time. And where those dots intersect and join together, that's showing you where those galaxies merged together. And so if you add it up, that final galaxy at the end, at the very top left, it has swallowed every one of those lines, dozens of galaxies during its lifetime, either directly or by swallowing the galaxies that had previously swallowed the little galaxies. So it's like I say, a hierarchical process. Little galaxies merge to make mid-sized galaxies. Mid-sized galaxies then merge to form big galaxies, and big galaxies swallow everything. And that merging is really essential if we're going to explain the formation of galaxies, because we actually have this amazing power with astrophysics. If you look far away, because of the finite speed of light, you're actually looking back in time. So with big telescopes, so the Hubble Space Telescope, if you look far enough away, you can actually see what galaxies looked like in the past. And so people have done that, and some work by Ian van der Wel here is a perfect example of this. And all I want you to really focus on this plot is that it's a plot of the size of a galaxy, how extended it is on the y-axis, and how big it is, how massive it is on the x-axis. And the black lines there, they show you what the relationship between size and mass was for spiral galaxies and for red and dead galaxies. Dead galaxies are ones in which there are no more stars being born. And you can see they have different relations, but they both have overall the same trend. If you want a bigger galaxy, a more massive galaxy, it will be larger in size. But what was found that was interesting was that as you go back in time, and you can see you've got little galaxies down there, and you've got the really giant galaxies up that end of the plot. What was interesting that was found, though, was that as you go back in time, those galaxies at fixed size are smaller, at fixed mass, sorry, are smaller. And in fact, if you pick a galaxy at a redshift of almost 3, which is about 11 billion years ago, and you compare it to one of the same mass about today, the one today will be about 5 times more extended than it would have been 11 billion years ago. And why that's interesting is because that is true of the galaxies that aren't forming stars and which have not formed stars since then. All of the stars in those red and dead galaxies are old. They haven't formed stars in 11 billion years, yet somehow they've got bigger over that time without them forming a single new star. So something is acting to puff them up, to make them more extended over time. And so simulations have shown, and this is some work that my PhD student did that was very nice, that showed that actually most of that expansion can be explained as the result of what we call dry mergers. And a dry merger is where you just take 2 of those dead galaxies and cram them together. You don't form any new stars, but you've increased the mass and you'll also make the galaxy bigger. And because you get this weird effect, or not a weird effect, but a natural effect that the stars you add to a galaxy preferentially get added to the outside, you also get a trend that the more at fixed mass, the more extended galaxies are the ones that have eaten the most other little galaxies, and the most amount of mass from other galaxies. And what this plot shows from the color scale is that when you get to the very biggest galaxies, almost 80 or 90% of the stars in those galaxies actually were not born in the galaxies you see them in today. They were formed in totally distinct galaxies, and then the big galaxies stole at some point in the last 11 billion years. And so that's what this plot here is showing. It's again just showing you mass against the fraction of stars that a galaxy has stolen. And you can see that for the lowest mass galaxies, you expect maybe 5 or 10% of their mass is acquired from other galaxies. But for the biggest galaxies, maybe 80% of their stars came from somewhere else. So you have your little galaxy down there, maybe 10, 20% of its mass has been stolen. The big galaxies up there again, 80, 90% of their stars were born elsewhere. Now, the problem from this, problem here, really, if you're an observational astronomer like me, is that all of this is really coming from simulations, or we're inferring it from very indirect methods. So the question is, observationally, is there some way that I can go out and measure this and prove that this is true? And in the end, in the Milky Way, the answer is yes, it's actually relatively straightforward to do that. We have a satellite in orbit now called the Gaia satellite, and it is in the process of mapping the distances, the positions of over 1 billion stars in our galaxy. So about 1/200th of the total number. And it does that using the parallax method, which is where it takes images of the sky 6 months apart, and then because the Earth will be on the opposite side of its orbit 6 months apart, it will have a slightly different viewpoint, and the stars will appear to move back and forward relative to the background stars. And so if you do that continuously, you can work out the distances to all of those stars. And he says actually made a nice little animation that shows you what that would look like. So it's going to show you, there's a view towards the Milky Way, and then this is now going to start moving those stars at a very exaggerated, by a very exaggerated amount, to show you how they would appear to vary in position across the sky, because in effect your satellite is changing its position over the course of the year. And you can see that the closer stars, they will have a larger parallax, they'll move back and forward more, and that's how you're able to infer how close they are, their distance. So when people combine that amazing level of detail, 1 billion stars with accurate distances, probably more than 1 billion by the time they're done, they can go out and get spectroscopy for millions of those stars. So that's where you take the light of the star, and instead of just asking what color it is or how bright it is, you split that light with effectively a prism, and you look for the chemical fingerprints of different elements in it. And people have done that now for millions of stars. And what they've been able to find is that there are all these families of very unusual stars out in the halo of our galaxy. So each of these color-coded sets of points, they're different families of stars. And those stars have the same chemistry, and they are moving with the same types of velocities and in the same directions. So they stand out very clearly amongst the background. And what we think is going on is that these are stellar streams. And so this shows you a simulation that was done for a different galaxy, but it shows you the basic idea. You have a dwarf galaxy come too close to a big galaxy like the Milky Way, and then the gravity of the Milky Way starts to raise tides in the lower mass galaxy. And those tides start to tear the stars from the dwarf galaxy, both forward in the forward direction of its motion and in the back direction, and they form what are known as tidal tails. So what we are seeing around the Milky Way in that map there are tidal tails. And to give you a sort of slightly different view, this is in effect what we're seeing. So around the Milky Way, we already have detected the signatures of around 20 different dwarf galaxies that are being destroyed currently. The majority, it would seem that the majority of stars, once you get a little bit above the disk of the Milky Way, the majority of stars out there probably came from dwarf galaxies that drifted a little bit too close to the Milky Way, then were destroyed. So in the Milky Way, we're actually in the process of detecting this process of what we call galactic cannibalism, the Milky Way eating its neighboring galaxies. But, of course, statistics of a sample of 1 is fairly dodgy. So we really would like to do a bit better. And in fact, we really need to do a bit better, because if we go back to that plot that we saw before, if we actually look at the mass of the Milky Way, even the simulations tell us that the expected accreted fraction of stars that the Milky Way should have could vary between 4% and 40%. So measuring a single value for a single galaxy really doesn't actually tell us very much at all. It's nice to have, but it's not going to constrain these models very much. So we need to do better. We need to look at other galaxies. So is there any hope of being able to do what we have done for the Milky Way for other galaxies? And the answer to that is no, absolutely not. We can only really resolve individual stars in the nearest galaxies. And even then, we can only resolve the brightest stars. And even then, they're still not bright enough for us to get the really good quality spectroscopy we need to be able to do those analyses. And there's a simple reason is galaxies are very far away. As you move them further and further away, the stars naturally, of course, get closer and closer together relative to our point of view, and they essentially get mushed together, and we just can't resolve them into individual stars. You just start to see everything as a blur and as the sum of the light of not one star, but hundreds, thousands, even millions of them. So we'll never get the detail that we have for the Milky Way, but we can still make some pretty impressive progress. One of the other things that you can do, and people have done, is to actually just go out and look not for the individual stars of the stream, but to try and just get the integrated light of the stream, to see it as an arc across the sky. And one of the funny things, the quirks about this is you might think you'd need the biggest telescopes in the world to do this because these features will be incredibly faint. But it turns out actually small amateur telescopes turn out to be better than the very biggest telescopes on Earth. And the reason for that's quite amusing. It's because the modern astronomical telescopes, the big ones, are really complicated. They use lots of mirrors and the light reflects off lots of different surfaces. And as it's doing that, some fraction of the light gets scattered and then just gives you a sort of diffuse glow that messes up your ability to detect very faint sources. So it's much better actually to use these arrays of telephoto lenses because they actually just have basically a single lens or two at most and a camera. And therefore there's much less ability for the light to go places you don't want it to go. And doing this, people have put arrays of these small sort of 10, 20 centimeter at most telephoto lenses together, and they've managed to detect stellar streams around many other galaxies. So you can see one on the right there, and they're actually detecting features down to 29 magnitudes per square arc second on the magnitude scale, which, if you're not au fait with the magnitude scale, is about 1 billion times fainter than the human eye can ever detect. And people are now actually starting surveys of thousands and thousands of galaxies looking for these streams. And you can see that they're already finding them. In fact, the results seem to show that as long as you're willing to image for long enough, and as long as you're able to go deep enough, you will find these features around essentially every galaxy out there. The slight downside with this method is that it's really, really hard to do. You need very, very good optics, and you need a really, really dark sight. And sadly, there are fewer and fewer of those left on Earth. Even then, all you're able to do is detect the very brightest streams. And those streams will not be very long-lived. After a few 100 million years, which admittedly sounds like a long time, but in this, astronomical terms is quite short. After a few 100 million years, those streams have wrapped around the galaxy so many times, it just becomes a sort of uniform glow, and you can't actually pick them out as distinct structures. On top of that, all you can ever really do is measure that there's some light there. It's so faint, you'll never be able to actually learn anything about the populations of the streams. You'll never be able to work out how old stars in them are or what their chemistry is like. They're just orders of magnitude too faint to do that. So the question is, can we do something better, or not better, but alternative? Could we, instead of looking at all of these things and trying to resolve structures, can we not just make use of that mushed together mess of all of the different stars in a galaxy? So this just gives you an example. This is the Sombrero galaxy, a very famous nearby S0 galaxy. But if we had the ability and we could zoom in enough, we would see that any region of that image was made up of many stars and many different ages and chemical abundances. And the question is, can we then recover that without having to have that resolution? And the answer is yes, to a large extent we can, using a technique called stellar population synthesis, which is where we model how the light of a population of stars will change over time. And I like talking about this when I'm talking about galaxies because it's a perfect distillation of everything about how stars live. So it's a way of bringing together the branches of stellar astrophysics and galaxy astrophysics. So SPS models have a relatively straightforward set of procedures. What we know from observing star-forming regions in the Milky Way is that at birth, not all stars are equal. They actually form with a range of masses. And we call the distribution of those masses the initial mass function. And it's the very first ingredient of an SPS model. The IMF, as far as we can tell, is basically constant across the Milky Way, and we hope across other galaxies to a certain extent. This plot just shows you different star-forming regions in the Milky Way, and all you're meant to take away from it is that the slope of those lines is pretty similar. And the result that comes out of these plots is that there are many, many more low-mass stars than there are high-mass stars. So for every 100 solar mass star, there might be tens of thousands, hundreds of thousands of 0.1 solar mass stars, for example. So many more low mass stars than there are high mass stars. And that is one of the determining factors that will affect how that population of stars will look over time. Now, why is that? That is because stars have some nice properties, nice scaling relations, we say, which are related all ultimately back to their mass, to how heavy they are at birth. So at birth, all stars lie on what we call the main sequence. And that's because fundamentally they are all doing the same thing. They're burning hydrogen fuel into helium in their cores. And the mass then will determine things like what the temperature of the surface of the star will be. So on this plot, which is a plot of luminosity against temperature, you can see the numbers there, 120 all the way down to 0.1, they're the mass of the stars at birth. And so a 120 solar mass star, it has a surface temperature of about 50,000 Kelvin, which makes it a very, very blue star. Whereas the very cool low mass stars, they're at about 0.1 solar masses, their surface temperature will be below 3,000 Kelvin, which makes them very dull orangey red stars. And of course, that color will then, when summed together, influence the color of your galaxy. If it's mostly made up of those low mass stars, your galaxy would be red. If it's mostly made up of those high mass stars, your galaxy would be blue. And the other thing, and so this is just an example, you can see I actually have put to scale one of those low mass stars near 0.1 and one of the high mass stars near 120 solar masses, just to show you the sort of size scale they have. And bear in mind, this is not the full range of star sizes. The stars get even bigger when they eventually evolve off the main sequence. They'll expand many times above the current sizes you see there. Now, the other thing that the mass determines, and this is now just a plot of mass against luminosity, how much light it gives out, is the fact that the mass and the luminosity are very tightly related. So if you look there at 10 to the minus 1, that's 0.1 solar masses. So it's 10% the mass of the sun. And a star down there is about 10,000 times fainter than the sun. Whereas at the other end, stars over 10 or 20 or 30 solar masses, they might be 10,000 times brighter than the sun. And so you see that if you double the solar, the mass of your star, you're not doubling the luminosity. You're actually increasing it by a factor of 8 or more. So this is a really important factor when we're doing an SPS model, as we'll see. The other thing that the mass determines is what the star's spectrum will look like. So we take the light of the star and then we break it up with a prism. And when we look at it, they will look very different depending on how heavy the stars are. So these stars, these different spectra, the different colors are from the top, very high mass stars down to very low mass stars. And you can see that the features in the spectra change. And you can also see the peak of the spectrum moves to the right, the highest point in the spectrum. And that's just because the surface temperature of the star is changing. And as that happens, your color of your star slides to the right and the star becomes redder. And then the other important factor that the mass of a star really affects is how long that star will live. And the range here is just enormous. So if you have a 120 solar mass star, it might live around 3 or 4, maybe a few more than that, million years, but certainly less than 10 million years. If you go to the other extreme of a 0.1 solar mass star, it can actually live for something like 12 trillion years. And of course, the sun at 1 solar mass will live for 10 billion years. So we have factors of millions in difference in the ages that these stars will live. The high mass stars, even though they've got more fuel, they live much, much shorter lives because they're so profligate with that fuel. That 120 solar mass star, it's 120 times more massive than the sun, but it's 1,000,000 times brighter. So in other words, it burns through its fuel 1,000,000 times faster than the sun. And so we have this effect that because the age of a star, the lifespan of a star is dependent on its mass, you will get an effect that when you stop forming stars, your massive stars will die first, and then you will get progressively lower and lower mass stars dying over time. And that will naturally change the color, the luminosity, and what the spectrum of your population of stars look like, as we'll see. And then the final thing the mass will determine will be how that star dies. So if you're a middling star like the sun, you'll go out like this as a planetary nebulae, where your star essentially has a coughing fit lasting 10,000 years or so, and the core of the star that was doing the hydrogen to helium fusion, that's about 10% of the mass of the star. It gets left behind as a white dwarf, and the remaining 90% of the star gets coughed back up into space, where of course it can be recycled into new stars and new planets. If, however, you're a bit heavier than the sun, a few solar masses or more, well, 8 solar masses or more, shall we say, they would explode as a supernova. And it's the supernova that do a lot of the chemical enrichment work of the universe, because it's in supernova that you produce many of the chemical elements. So the ratio of your high mass to your low mass stars will affect how rapidly the universe gets more complicated in terms of its chemistry. More high mass stars, you will get more chemically complex faster. And so that's an extra parameter in all of these models that we have to be aware of, and that's the amount of elements other than hydrogen or helium that are present. And we call that the metallicity. And that's because this is the periodic table you're probably familiar with from school, but this is the periodic table for astronomers. We have hydrogen, helium, and everything else is a metal. And in part, that's because if we're talking about mass fractions of the material in the universe, 74% of the mass of chemicals, shall we say, in the universe, elements in the universe, is in the form of hydrogen, about 24% in the form of helium, and about 2% is in the form of everything else. The reason we care about that, though, is the chemistry, the chemicals that are elements that are available will change the spectrum dramatically. So in this plot, I'm just plotting the spectrum of effectively 3 stars like the sun. The first solid line, that is an approximation of what a solar spectrum would look like if the sun didn't have any chemical elements other than hydrogen or helium. In other words, if it was one of the very first stars born after the Big Bang. And then the other 2 are, the red one is an example of a star very like the sun, almost exactly the same amount of chemical elements as the sun. And then the other one is one that has a few factors less metals than the sun. And you can see that the shape of the spectrum changes quite a lot based on how much stuff you have in it. And that's because those chemical elements are interacting with the light, and they're absorbing the light and creating these absorption lines and giving away their presence. And so much of what we do in astrophysics is actually measuring those absorption lines to work out just how much hydrogen is present, how much helium, how much iron, how much magnesium, that kind of thing. So the SPS recipe, you choose an initial mass function to give you a zero age main sequence. And so on the left there, we have our zero age main sequence, and I've marked the sun as that circle with a dot in it. And that's what the main sequence of a population of stars would look like at about 60 million years after it had been born. Then you choose a metallicity for that population, and you use the IMF and metallicity to populate that HR diagram. And what do I mean by that? Well, what I mean is you say, okay, I'm going to produce a bunch of low mass stars based on the IMF. I'm going to produce fewer mid-mass stars, and then I'm going to produce a handful of the high mass stars. Then you tag each of those stars with a spectrum that that star would have. So the B-type stars, the hot massive stars, get that kind of spectrum. The A-type stars get that spectrum. The F-type stars get that one. The solar stars get that one, and so on and so forth. And then you just add them all up. You add all of those spectra up in the correct proportion for the number of stars that are present and how bright each star is. And when you do that, you get the sum of the light of what could be 1 million different stars. So there we've done that for that population of 63 million-year-old stars. And what you can see is for a 63 mega-year-old population, that spectrum actually looks very like the spectrum of the B stars. And that's because those B stars are the most massive stars still alive at that point, and they're therefore the brightest. So they're producing most of the light at that stage. But we can then evolve our model on and say, well, okay, let's now look at what that population would look like after 100 million years. Well, some of the high mass stars have now died. So we remove them from the sun. And that means that the spectrum will get fainter. And then we say, well, what about 500 million years? Again, those high mass stars have died. Some of them have evolved off to become evolved stars. So we'll populate that branch, sum it up, and we get the green plot. Then we do 1 billion years old, 5 billion years old, and 10 billion years old. And so those spectra on the right are the spectra that you would get if you had just ensemble, maybe 100,000 stars, all born with the same metallicity at the same time, and then you just evolved them on their own over time. And the really amazing thing that has been developed over the last few years has been the ability to use a huge amount of computer power and to take those different models of what those populations of stars look like and work out which combinations of them best fit the spectra that you're getting from your galaxies. So you go to your big telescope, you get a spectrum of a galaxy, then you throw your relatively powerful computer and hundreds of models of what stellar population should be for different ages, different metallicities, and then it selects which ones best fit the data. And so our team, led by a student back at MPIA, one of my former institutes, worked out a way of how to do this with existing software, but to do it really, really accurately. And so this is just a demonstration of how this technique's improved. The plot on the left there shows you the distribution of ages of stars and the different chemistry each of those groups of stars had that we input. And then we try and fit it to recover what we put in, and we check, did we get out what we put in? And if you use the original standard approach, you'd get this result, which overall it gives you the right sort of average age and average metallicity, but it doesn't look a lot like the plot on the left. So what Alina was able to do was come up with a way that we could get this. And even though it still looks a bit different, it's actually right to within a few percent. So what that means is from a single, in principle, a single spectrum from a galaxy, you can decompose what would have been the light of millions of stars into the different types of star that are present in there, even with just a single spectrum. The real insight, the real breakthrough that has allowed us to push this even further, though, was that we could look at the simulations, take a God's eye view, and actually look at, for individual galaxies that were merged into a big simulated galaxy, what did their stars look like? Were they all the same, or did they have different properties? And what we actually found was that galaxies of different mass had stars that were very distinct. We could actually separate them in terms of their age and metallicity. They lived in different parts of the plot. And the reason for that comes down to a really nice bit of galactic astrophysics. So this is just a plot of the mass of a galaxy against the size of a galaxy, and just look at the colored points that run from left to right. And what you see is they are the galaxies. There are low mass galaxies with maybe 1,000, 10,000 stars in them. And then there are high mass galaxies with hundreds of billions of stars in them. And the average metallicity increases as your galaxy mass increases. So the big heavy galaxies, the really massive ones, they are very, very chemically complex. Whereas the low mass galaxies, they're really quite chemically simple. And the reason for that is gravity. When you form stars, the big ones go supernova, they go bang. And if you live in a low mass galaxy, those supernova can actually produce enough energy that they blast their material, including all of those nice new chemical elements you've created, right out into intergalactic space, where they're no use to anyone. And so this is M82, which is a nearby galaxy that we imaged with our telescope. And the red streamers you're seeing there is hydrogen gas being blasted out of this galaxy because it's going through what we call a starburst and because it's low mass. Now that only happens to those very dinky little galaxies. The really, really big galaxies, they're so massive, they have so much gravity that that material will get blasted out by the supernova, but then it gets dragged back in again. And because it's enriched in metals, those metals then go into the next generation of stars and make them even more metal rich. So what we're seeing here is that big galaxies are able to hold on to more of the material that their supernova produce. And therefore they get more and more chemically complex over time. Whereas the low mass ones have a real struggle to keep anything that their supernova produce. And so this leads to an interesting trend that the mass metallicity relation depends on galaxy mass. So low mass galaxies can never get as metal rich as high mass galaxies. And furthermore, they take longer to build up their mass because they have less gravity. So they're pulling in less material, they're pulling in less gas. And so you get these tracks, these different colored tracks, which tell you how the chemistry of a galaxy of certain masses should evolve with time. And because you can draw these on these plots that are similar, are model fits recover, you can actually work out that certain stars must have come from galaxies of certain masses. Even though they're in maybe a galaxy of 10 to the 11 today, you can look at them and say, well, that galaxy is very young and metal poor. There's no way it could have been born in the galaxy we currently see it in. So my PhD student, Tom, has tested this method using a galaxy called NGC 7135. And the reason we did that was because it was known to have a merger. So if you look on the image on the right, you can actually see the stellar stream sticking out of the galaxy up to the top left. And actually you can see a plume of material towards the bottom edge of that blue outline, which shows you where we have spectra from. And Tom used this instrument Muse, which you can see there looks like something from the Matrix. It's about the size of, you know, a car, and it's dozens of spectrographs all stuck together that allow you to get not just one spectrum at a time, but thousands of them, so that you can tile them and you can map across a galaxy to work out its properties as a function of space across the galaxy. So Tom was able to do that, and he was able to apply our models to them. And when he did that, it was very easy to split that galaxy into 3 different components. We were able to find the signature of the ongoing merger, which tracked exactly where those plumes were seen, including actually the center of that galaxy that's currently being destroyed. We also found the stars of the main galaxy as it currently is, and they're all basically centrally concentrated where they should be for the original galaxy. And then, a bit to our surprise, we also found evidence for an ancient merger that happened a long time ago, just buried in the signal. So in that example, we can show that the stellar populations of those stars correlate with their position in exactly the way you would expect of galaxies that have merged into the bigger galaxy we see today.
5 minutes, Mark.
Well, that's great, because I've got like 3 slides left. So, impressed by that Tom's now looked at a much larger sample of galaxies, and in all cases we see that the fraction of stars that we think of as coming from outside, from an external galaxy, increases as you go further out in the host galaxy. So that's what that plot there shows. It shows 13 or 14 different galaxies. The color coding is the fraction of stars that were originally from somewhere else. So purple means basically none, and yellow means basically all of them. And then he split it by the center of the galaxy, which we expect to be dominated by the stars that were born in that galaxy, and then the galaxy outskirts. And so you can see that for every galaxy, as you go from the left panel to the right panel, the color becomes lighter, it turns more yellow, which is indicating that the fraction of stars that were stolen from another galaxy has increased. And of course, that's exactly what the merging picture would tell us is going on. On top of that, you can also see that if we look at fixed mass, and so basically go from the bottom upwards, you also see a trend that the higher galaxies have a larger fraction of stars that were stolen than the lower galaxies. So the more extended galaxies have more stars from somewhere else. And again, that was what the simulations said as well. As you go up in size, the more extended galaxies are more extended because they've stolen more stuff and added it to their outskirts, which makes them physically bigger. So that's really a very exciting result, because this has never been seen before. And based on the results Tom's getting, they look perfectly in line with what the simulations would predict. And they obviously have really huge scope to apply this method to basically any galaxy you might want to. And it doesn't even take a huge amount of telescope time. Per galaxy, you needed about an hour, which, if you're talking about big astronomical observations these days, is almost nothing. So, my conclusions. Well, simulations have shown, and I think we can be fairly confident that it's true, that galaxies have to be thought of as forming from and through 2 distinct but interrelated processes, which is where they've created their own stars and then they've acquired other stars from other galaxies. We now have multiple different approaches that allow us to see this process play out. And so far, there's the observations seem to actually support basically exactly what the simulations predict. The Milky Way is currently eating of order of 20 galaxies, but over its lifetime, that number is going to be probably hundreds. And if you go to the really most extreme galaxies, the ones that sort of dominate the center of galaxy clusters, like M87, the one with the famous big black hole at its center, that will be 90% composed of stars that were formed in galaxies more like the Milky Way and were then just stolen by that big galaxy. So we're sort of on the cusp now of, we've had a revolution in the technology. In the next few years, big telescopes like the one you see there, the ELT, will come online. And with things like the ELT, we'll actually be able to use this same approach, not just for galaxies in the nearby universe, but for galaxies further back, and actually track these mergers as they occur back through cosmic time. So that's quite exciting and something I'm looking forward to probably around the year 2025. So not too long now. Other than that, I will stop and will gladly take any questions.
Thank you very much, Mark. That was great. That was really really impressive. One of the things that struck me, I don't know if it struck other members of the audience, was that we started out by calling the Milky Way just a band of diffuse light.
Yeah.
And you finished up by measuring the spectra, essentially, of the diffuse light of distant galaxies.
Exactly.
So from separating that diffuse light into individual stars to going back to now where we can handle the diffuse light again.
Yeah, until we have a telescope with a 100-meter mirror, we're going to be dealing with the diffuse light of other galaxies.
So it's funny how things sometimes appear to go around in circles.
Yeah, circular.
I suspect you didn't see it, but I made a rude comment in the chat about your favourite instrument looking like a piece of modern art made out of recycled bicycles. But yes. Probably just as well you didn't see it.
Yeah,
so I'm going to throw
a piece of art.
I'm going to throw the floor open to questions. There are multiple ways you can ask questions. You can either just switch your microphone on and shout up, or type a question into the chat. For those of you who don't know how to use the chat, it's at the top right hand side of your screen, the speech bubble. If you click on that, and then you can type into the bottom right hand side, or you can put your hand up, which is the symbol next to the speech bubble. So please don't be shy. Please feel free to ask any questions you'd like. So over to the audience.
Dr. Norris, thanks very much for that. It's Bob Mount from Southport Astronomical Society.
Welcome, Bob.
Hello there. I thought that was a fantastic presentation. I give talks on such things, but nothing like as up to date as yours, of course. But I did recognise one or two of the things you said. I always emphasise the importance of mass. It's all about mass, you know. But
mass is destiny.
It does. And the question is that, am I right in thinking then, does that in some way then explain why it is that Andromeda is physically bigger than Milky Way, but has got a lot less mass? It also has a lot more galaxies and very large globular clusters and so on around it, much more than the Milky Way. And of course, the Milky Way produces more stars than the Andromeda.
So there's an interesting, the mass of Andromeda has been a long-running debate, but at the minute, the latest measurement is that it's about 50% more massive than the Milky Way, which does actually fit. So what's going on there is actually kind of related to what I was talking about, which is how do you work out what the mass of a galaxy is, especially its stars? well, you actually use basically the approach I was talking about there. You look at its light and you assign what's known as a mass to light ratio, right? Which is where you say, if I had one solar mass, if the sun, for example, by definition, it's one solar mass and it has one solar luminosity, right? But a high mass star might have a mass to light ratio of 0.05 because it's so much more luminous per unit mass. But then a low mass star might have a mass to light ratio 5 times higher than the sun because it's a very low mass star and it's putting out very little light. And the problem with Andromeda is it is a bigger galaxy, and it's a little bit, so the Milky Way is at this really interesting point. It's at the most efficient mass for turning gas into stars, it turns out. So the Milky Way is chugging along at this constant rate, forming stars at a rate of about 1 solar mass per year. And as far as we can tell, it's done that for 10 billion years without interruption, right? Just chugging along quite happily. The Andromeda Galaxy is a little bit more massive, and it's on that sort of slope where you start to run into the problem where it's a little bit too massive. It can't form stars as efficiently, potentially, and it might therefore have a slightly, its population will be weighted towards older stars, and therefore its mass to light ratio will be higher. And old measurements, I think, just assumed the Milky Way's mass to light ratio and applied it to Andromeda, and that would make it have the wrong mass, basically. Right. They were underestimating the mass of stars, essentially. So the whole thing's all circularly related, but it makes sense. If it's 50% bigger, it makes sense because it's got the right number of globulars then, and it's got the right number of satellites, and the motions of the satellites also make sense from a dynamical point of view. Right. So I think that problem's gone away, but I haven't checked in the last year.
Okay. Thank you very much. Thank you.
So we've got a question mark in the chat from Nikki. If the universe is expanding and galaxies are moving further apart, and I love this phrase, will the galaxy banquets eventually end? That's a lovely phrase, Nikki. Or has it happened already?
Yes, is the answer to that, both of them. So that's a very good question. If I had a plot of, I do have a plot, just not in this talk. There's a plot which shows you the rate at which stars were formed per unit volume of the universe, right, as a function of time. And what it shows is the universe peaked in the amount of star formation it was doing about 8 or 9 billion years ago. Ever since, the amount of stars being formed has dropped off. And that's because, for exactly the reason you point out, the universe is expanding. It's getting harder and harder for galaxies to get fresh gas, and therefore they're all basically gradually winding down. The real party days of the universe were in the period of, say, 13 billion years to about 10 billion years ago, and it's been downhill ever since. And sadly, I can't give you any bright or happy news there. It's just going to get worse until there's nothing left.
If you want to Google it, that picture that Mark's talking about, Nikki, it's referred to as the Lilly-Maddow plot. Lilly as in Lily, and Maddow as in Madau. If you want to have a look at that, it shows how it goes up quite rapidly in the early parts of the universe, and then, as Mark says, after a wild party, it's come down ever since. So we've got a question, Mark, from Stephen Nichols. Why do higher mass galaxies not make more stars than the Milky Way? That's a good question.
So that's a great question, and it's a one that I can't give you a really good answer to. There's two schools of thought, right? Because there's two influences on a galaxy. There's what's known as the secular influences, which are the effects due to the galaxy itself, its own mass, its own properties. Then there's the effects which are known as environmental. They're to do with where you've put that galaxy. So, for example, one of the reasons why very high mass galaxies aren't forming many stars now is that most of them are found in galaxy clusters. And galaxy clusters have these really hot halos of gas, millions of degrees, heated up by the black holes of the big galaxies and just by the gravitational collapse energy as things fall in. And that gas just is so hot, it will not allow any gas to cool and form stars. And so they've been strangled. It's literally called strangulation. The galaxies and the galaxy clusters are strangled. They were able to form stars for the first few billion years of the history of the universe. They got quite big then because at the very early point in the history of the universe was much denser, and therefore it was easier to pull all that gas together. And they also lived at the very overdense regions. But then once that halo went hot, it stopped all star formation, and all they could do after that point was just acquire stars from other existing galaxies. And any galaxy that falls into a galaxy cluster today that is forming stars as it falls in, it finds that its gas gets ripped out of it, and it gets its own star formation stopped within a few 100 million years or so. So that's part of the reason that the high mass galaxies on average are in denser, and the very high mass galaxies are in dense environments, which just prevent star formation. The other one is that there's the theories to do with how star formation occurs in big galaxies like the Milky Way, and it's to do with the structures of the galaxies. And I'm really not an expert on that stuff, but it's to do with if you go lower mass, you can't form stars very, very efficiently because, again, you're low mass, and every time you form a big star, it goes supernova and it blows all your gas away. So that slows you down. Every time you try and form some stars, you blow your gas apart. And then on the high mass end, there's something to do with the way spiralons work and sweep up gas and all. Derek probably knows more about this than I do. That goes on there. But I think the biggest reason is just environmental. You don't want to be in a galaxy cluster, basically.
And if I can just add to Mark's comments, that in order for a parcel of gas to collapse and to form a star, it needs to lose a lot of its heat energy, because the heat energy basically supports it, holds it up. If you remember your school sort of science lessons and learning about Brownian motion, where you see it's the motion of the molecules of the gas, and the hotter they are, the more they're moving about, and so the harder it is for gravity to collapse them. So hopefully that answers your question, Stephen. Nikki has said, Mark, thank you for a brilliant presentation. Nigel Morton has said, do all galaxies have a black hole in the centre, Mark?
The answer to that seems to be probably. We are at a strange point where every massive galaxy we've looked at has one, pretty much for sure. So once you're getting 10 to the 10 solar masses or above, they seem to all have them. Below that, the problem becomes that the black holes scale with galaxy mass. So the larger or more massive your galaxy, the bigger your black hole is. And once you get to lower mass galaxies, the black holes themselves actually become so low mass that they're difficult to detect. So we have this sort of, pardon me, intermediate mass black hole range, we call it, which is not well sampled because they're observationally very difficult to find. So they're black holes that are sort of less massive than about 100,000 solar masses, but bigger than the 100 solar mass black holes that you get from a big star that died. And it's just it's almost certainly just an observational effect that if you look at a 10 to the 8 galaxy, you only expect a 10,000 or 100,000 solar mass black hole, and observationally they're really hard to see at present. So I think the answer is almost certainly yes.
Thanks a lot, Mark.